Hello, in this video I'm going to be solving exercise 7.2.4 from Jiří Lebel's notes on Diffy Qs. So in this problem, we need to use power series methods to solve this ODE here, and they say at the point x not equal 0. So first, a bit of recollection. So when we say solve at the point, say more generally, x not equals a. So whenever we hear this phrase, solving using power series at this point, what we mean is we need to find a power series expansion centered at the point a. So here we need to assume that y of x has the form n from 0 to infinity, Cn, and then by the center, what we mean is that our powers of x are instead going to be powers x minus a for our series expansion. So for us, a is equal to 0. So we're going to assume a series solution of the form Cn x to the n. Now, to figure out or to determine these coefficients, which is going to be the ultimate goal for this method, we need to figure out what y double prime is. Now, with power series, we can calculate derivatives just by differentiating termwise. So if we want to calculate the second derivative, and I even write it this way. If we want to calculate the second derivative of this power series, we can just do it term by term. So, and this is much easier to see if we write out the whole power series. So c1 plus c1x plus c2x squared plus c3x cubed plus on and on and on. Well, when we take derivatives, this is going to be d dx. So now this goes away, and we're left with c1 plus 2c2 plus 3c3. Oh, I forgot the x. X plus 3c3x squared plus 4c4x to the fourth, on and on and on. And I'm going to take another derivative, so this will be 2c2 plus 2 times 3c3x plus, and oh, this is supposed to be, there we go, sorry, that was supposed to be a cubed. And this will be 3 times 4 c4 x squared, on and on. So this went to 0, oops. This went to 0, we took the derivative of this, took the derivative of this, took the derivative of this. And we can see that the pattern in general for our series is if we start from 2 to infinity, it really helps to add this invisible 1 right here. In general, the pattern is that we're doing n minus 1 times n, and then x to the n minus 2. Okay, so now we have this series. So now we're going to plug this into our ODE. When we do this, 0 is going to be n from 2 to infinity, n minus 1. Oh, I forgot the coefficients here. So this is Cn x to the n minus 2. There we go. And then we're going to do x squared, and we're going to plug in our series for y. So this will be Cn x to the n. And we're going to want to bring in this exponent into this x. So this will be n from 2 to infinity, n minus 1, Cn x to the n minus 2, plus n from 0 to infinity, Cn x to the n plus 2. Okay, so let me copy this so we can go to another page. No, not color, oops. copy. Okay, so we have this expression. So to be able to simplify this right here, we're going to need to get the indices aligned. So to this end, we're going to do, it's called reindexing. So first thing is I'm going to let k equal n plus 2. So first I'm going to work on this series. Then since n goes from 0 to infinity, well, we see that k has to go from 2 to infinity. So if I plug in 0, I get k equals 2. If I plug in 1, I get k equals 3, and so on. We have k is greater than or equal to 2. So our series becomes, and from 2 to infinity, n minus 1, cn x to the n minus 2, plus k now from 2 to infinity of c. And then if we solve for n right here, we're going to get c k minus 2 x to the k. And so now we have this series here. Okay. So now it looks like the bottom indices match up. Don't worry about the k. I know the k's and the n's look different, but they're just dummy variables. So we can always change from one index to another. But there's a problem here. We can't just add up these series right away because here we have x to the n minus 2. And if we change this from k to n, we would have just x to the n here when it should be x to the n minus 2. So to fix that, I'm going to do now an index shift on the first series. Or I'm going to re-index the first series. So here I'm going to let m equal n minus 2. Then because n is from 2 to infinity, so since n is at least 2, we have that m is at least 0. So if we change our indices, this will be sum from 0 to infinity, and we need to solve for n. And you know what, here I'll also write that this gives n equals k minus 2, and here n equals m plus 2. So if we plug in n equals m plus 2 into this series here, what do I get? I'm going to get m plus 2, m plus 1, cm plus 2, x to the m. And again, our other series is still the same. X to the k. Right? Okay. Why is this useful? Well, now you might notice that the powers of x are exactly the same, right? Oh, wait, I made a typo. Oops. That's supposed to be 2. Okay, so now we got the powers to be the same, but now notice that the bottom summation indices are different. Because we want to compare coefficients, we're going to want those indices to be the same. So what I'm going to do is I'm going to take out the first 2 terms for m equals 1 and m equals 2 from this series and isolate them, which gives me, so if I plug in m equals 0 right here, I get 0 plus 2, 0 plus 1, c 0 plus 2, x to the 0. And then I'm going to take out the m equals 1 term as well. 1 plus 2, 1 plus 1, c 1 plus 2, x to the 1. And then we have just the rest of our series. M from 2 to infinity, m plus 2, m plus 1, x to the m, plus the series from k to the infinity, ck minus 2, xk. And we can clean this up. So this becomes, so just cleaning up these coefficients here, we're going to get 2c2. And then x to the 0 is just 1. Great. And then our other coefficient is 2 times 3, or rather 3 times 2c3x plus, and now again, because these are dummy indices, and I'll write this in blue, I'm going to change to m. Now, it's important to know I'm not plugging in m equals n minus 2 into here. I'm not. I'm simply, all I'm going to do is, okay, let me first copy down my first series, m from 2 to infinity, m plus 2, m plus 1, x to the m. And then I'm going to copy down this exact same series, but I'm just replacing my k's with m's. Sorry. This series and this series are still the same because they still represent exactly the same sum. It doesn't matter what variable we use to sum over because at the end, they both represent the same thing that we're adding up. But now, what this lets us do, you might notice, is now we have 2c2 plus 6c3x plus, now we can combine the two series by just bringing the sigma out from both. We're going to get m plus 2, m plus 1. And if I factor out the x to the m from both terms, oh, I forgot my coefficients. Oops. Plus, my bad. If I factor out the x to the m from both, I'm going to get cm plus 2 plus cm minus 2x to the m. And again, all of this is equal to 0. So the only way, I'll write this out. So the only way for a power series to be 0 is if all its coefficients are 0. It's similar to how when you have a polynomial, the only way for that polynomial to be identically 0 is if all its coefficients are 0. So star, which I've labeled above, gives, well, we have that. So first off, this coefficient must be 0. Or rather, this coefficient, the whole thing. 6c3 must be 0. And then we get this, all of these must be 0. So m plus 2, m plus 1, cm plus 2 plus cm minus 2 must be 0, and this must hold for all m bigger than or equal to 2. Okay. In other words, all right, well, this just tells me that C2 is 0. This tells me that C3 is 0. So I get that C2 is 0, C3 is 0, and if I take my last equation here and I solve for Cm plus 2, I'm going to get that Cm plus 2 equals negative Cm minus 2 all over m plus 2, m plus 1. And this is for m bigger than or equal to 2. So, okay. To clean up this last equation here, I'm going to rewrite it in a bit. So I'm going to rewrite it a bit, sorry. So instead of doing this m plus 2, m minus 2 business, I'm going to give a name to this. So let L be the bigger of the indices, m plus 2, then because m is bigger than or equal to 2, we have that L is bigger than or equal to 4. So if we write this equation in terms of L, what do we get? We get that CL equals, okay, well, if L is m plus 2, then if I solve for m minus 2, this will be L minus 4, right? So this equation right here, which I'm going to call double star, becomes the following: negative CL minus 4 all over, and then m plus 2, once again, is L. And then m plus 1 is going to be L minus 1. And this holds, again, for L bigger than or equal to 4. Okay. And this is great because now this gives us a recipe to be able to figure out the bigger coefficients in terms of the previous coefficients. Okay. So the first thing I notice is because C2 is 0 and C3 is 0, it follows. So for example, notice how we're doing jumps of 4. We're going from L minus 4 to L. If I take 2 and I add 4 to it, I'm going to get that C6 equals negative C2, again from this formula here, all over. And then we're plugging in, well, we're plugging in 6 for L. So this will be 6 times 6 minus 1. But C2 is 0. So this is actually just going to be 0. Similarly, if I do, well, let's take 6 and add 4 to it again. So C10. This will be negative C6 all over 10 minus 1. Again, just plugging in 10 for L. And since C6 is 0, this is also 0. And in general, if we continue like this, if we continue the pattern, well, we're adding multiples of 4 to 2. So this tells me that C of 4n plus 2 equals 0 for all n bigger than or equal to 0. Similarly, since C3 is 0, well, now let's add 4 to 3. We get C7 equals negative C3 all over 7 minus 1, which again has to be 0 just because C3 is 0. If I add 4 to 7 once more, I get this. And this again has to be 0 because we just found that C7 is 0. And in general, the pattern is, well, you might see that we're doing 3, then we're doing 3 plus 4, then we're doing 3 plus 2 copies of 4. So this tells me that 4n plus 3, oh, oops. That these coefficients are 0 for all n. Okay, but what about the other coefficients? What about, so here we started with C2 and C3. What if we start, I'll write this in red. What if we start with C0 or C1? What's going to happen? Well, let's see. So let's start with C0. So if I add 4 to 0, I get C4. And this is going to be negative C0 over 4 minus 1. And note that we didn't get any information about C0 from our previous work over here. There's nothing that told us that C0 has to be 0 or any other number. So C0 can be arbitrary. Okay, so this is the simplest we can go. And actually, maybe we can write this a bit cleaner. C0 over 3 times 4. Likewise, C8, well, now we're just adding 4 to get 8. So this is negative C4 over 8. 8 minus 1. But if we plug in the formula we just got for C4, this will be negative 1 squared times C0 over, and then we have to multiply 3 times 4 and then 7 times 8. And in general, if you continue like this, you'll quickly notice a pattern. You'll notice that the 4nth coefficient is given by negative 1 to the n, C0, all over, and then we're doing 3 times 4 times 7 times 8, dot, dot, dots, and we're multiplying this all the way up to, let's see over here. So here we stop at 4n, so this goes up to 4n minus 1, 4n. And we add the 4n minus 1 because of like that 7 right there. 7 is 8 minus 1. So this is the general pattern for the 4n coefficients. Now let's see what happens if we start at C1. So adding 5, we get negative C1 over 5, 5 minus 1, which is negative C1 over 4 times 5. Okay. Again, nothing from our previous work imposed any conditions on C1, so C1 can be arbitrary. Now let's add 4 to 5, so we get C9. So this will be negative C5 over 9, 9 minus 1. But if we now plug in our formula for C5 into here, we get negative 1 squared C1 over 4 times 5 times 8 times 9. And here we get another pattern. We see that in general, so notice that these numbers look like 4n plus 1. And so in general, oh no, sorry, yeah, 4n plus 1. So in general, what we find is that this is negative 1 to the n, C1 over 4 times 5 times 8 times 9, dot, dot, dots. And we're going to multiply all the way up to 4n plus 1. Because you might notice, like for example here, this is our 4n plus 1, this is our 4n, this is our 4n plus 1, this is our 4n. And so, going back to our series, now that we know all the possible coefficients, well, again, this is our series, but we know that all but only the coefficients of this form and this form vanish. So our final solution is going to be, well, now we're just going to plug in these coefficients for these powers of x. So we get 1 minus, or sorry, we get C0 minus, so here I'm just plugging in all my coefficients back. It's minus C0 over, what's it? Oops. C0, and then C4 is 3 times 4, yeah, sorry. Plus C0 over 3 times 4 times 7 times 8, x to the 8, minus C0 over 3 times 4 times 7 times 8 times 11 times 12, x to the 12. On and on and on, and in general, the nth term of this series is this. This is going to be 4n minus 1, 4n, and when we're doing x to the 4n. And then we're also adding the terms corresponding to 4n plus 1. This is c1 minus c1 over, what are first 4, 5? X to the 5. Oh, this is x to the 1, sorry. c1x. There we go. Plus c1 over 4 times 5 times 8 times 9, x to the 9. Minus on, where in general the nth term is negative 1 to the n, c1 over 4 times 5 times 8 times 9, on none up to 4n plus 1, x to the 4n plus 1. And notice this is really nice because, oh, and I forgot to add plus dot 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 plus dot dot dot. And this is really nice because we can factor out the C0 and the C1 from each of these. And what we get is the following. So we get C0 and then 1 over 3 times 4 x to the 4th plus 1 over 3 times 4 times 7 times 8 x to the 8 minus dot 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 plus, where the nth term once again is this, 3 times 4 times 7 times 8, 4n minus 1, 4n, x to the 4n. And we can also factor out the c1 from the other series. We get x minus 1 over 4 times 5, x to the 5, and yeah. Plus 1 over 4 times 5 times 8 times 9, x to the 9, and then minus, where in general the nth term, as we found in the previous page, is 4 times 5 times 8 times 9, on non up to 4n plus 1. And so this would be the series solution for our problem. So if we wanted to make it more concise, we could let this be this first series here. I could call it y1 of x. And then actually, let me use different colors for that. So if we wanted to, we could give a name to this first series, call it y1 of x. And this second series, y2 of x. And then we could simplify this solution to this. But again, the series solution is this one above, where we actually write out the series. All right, that wraps up this video. If there are any questions, please feel free to leave a comment. Otherwise, I will see you all in the next video.